Hello everyone. In this part of the session, we are going to deal about changes in the states of matter. That is, how we can change a solid to a liquid or a liquid to a gaseous form or the reverse pathway. That is, a gaseous form to a liquid to a solid. We can also undergo a conversion from a solid to gaseous form directly without undergoing the intermediate liquid state, and also from gaseous state to the solid state. How can we do all these things? By changes in temperature and pressure conditions. Because these two conditions only can bring about changes in the particle arrangement, in the movement of the particles. So let's explore some new concepts. Hello everyone. When we want to change the state of matter, we should know about temperature, we should know about pressure conditions. The first thing that we can see over here are temperature and its unit. We know temperature has units like Celsius, Kelvin, Fahrenheit. So the Celsius temperature is under the name of Anders Celsius, the scientist, and Kelvin under the name of Lord William Thomson Kelvin. So Celsius scale of temperature is used in our everyday life. Kelvin scale, it's always used as the SI unit of temperature is Kelvin. So we don't write degree Kelvin. Please mark this, that we don't write degree Kelvin. We write degree Celsius. And what is the relation between degree Celsius and Kelvin? Temperature on Kelvin scale is equal to temperature on the Celsius scale plus 273. Why is it so? Because 0 degree Celsius is equal to 273 Kelvin. So we can see numericals over here, which is from the NCERT book itself. Convert the temperature and it's given 25 degrees Celsius. You have to convert it to Kelvin scale. Use the formula that Kelvin scale temperature is equal to whatever is given in degrees Celsius plus 273. We are using this formula and hence 25 degrees Celsius plus 273 gives us 298 Kelvin. So this was one of such example from NCERT. Next we can see, convert the temperature Kelvin to Celsius. Previously it was Celsius to Kelvin. Now Kelvin to Celsius. The same thing we will use this formula. Temperature on the Kelvin scale is equal to temperature on Celsius scale plus 273. So 300 is equal to x degrees Celsius plus 273. So from here we can find x, which is equal to 300 minus 273. What will be the unit? It is degrees Celsius. So to convert a temperature from Celsius to Kelvin, what we need to do? Celsius scale to Kelvin scale, we just need to add 273. To convert from Kelvin scale to Celsius scale, what we will do? We will subtract 273 from the Kelvin temperature. Now moving on to change of state. Change of state can be 3 physical states and their interconversion. Okay, we know these are the 3 states of matter, that is solid, liquid and vapor. So of what? Of course water. Water can exist as solid, that is ice form. It can exist as liquid, that is water, and gaseous form, which is steam. So these are what we are familiar with. We can change the physical state of the matter by changing the temperature and by changing the pressure. So let us see how we can do so. Next page, effect of change of temperature. One general thing I want to say to all of you, that is, when I want to change from a solid to a liquid state, I actually want to bring out a change where a very close packed structure is going to convert to comparatively loosely packed structure. So I want to increase the interparticle space and decrease the interparticle forces of attraction. This can be done by bringing the particles apart and by application of heat. This triangle sign goes for heat. So if I heat, then I can increase the interparticle distance. And this process by which I can actually convert a solid form to a liquid form is known as liquefaction, liquefaction. If I undergo the process of conversion of ice to water, then this is known as melting or fusion. So the process of conversion of ice to water or any solid to its liquid form is known as melting or fusion, and the temperature at which this conversion can take place at atmospheric pressure is known as melting point of that substance. We all know that the melting point of water, or I'll say melting point of ice, is 0 degrees Celsius, or rather the freezing point of water. Why I am telling the freezing point of water? Please keep in mind that the melting temperature and the freezing temperature is the same. The only difference lies in the process. When I say melting, I am converting solid to liquid. When I say freezing, I am converting liquid to the solid state. And you know that if I have to give heat for changing from a solid to a liquid state, I need to cool it to change it from a liquid to a solid state, and it is known as solidification or maybe freezing. So let us see. This is when solid is heated sufficiently, it changes its state and becomes what? Liquid, that we have already seen. And the temperature is known as what? At which this conversion is taking place is known as what? Melting point for solid to liquid state conversion. Okay. So the heat energy makes its particles vibrate more vigorously. And at the melting point, the particles of the solid have sufficient kinetic energy to overcome the forces of attraction and hence change its state. If it is overcoming the forces of attraction, means the particles are increasing the distance between them and hence going on to the liquid state. Next, if I even more heat, that is a liquid state, I'm again heating, and then I can go to the vapor phase or the gaseous state. Because when I'm heating it further, I'm increasing the kinetic energy even more and increasing the interparticle distance, decreasing the interparticle forces of attraction. And this process is known as boiling, or I can say vaporization. So the process in which a liquid substance changes into its gaseous form on heating is known as boiling or vaporization. Now vaporization and boiling, see, I'm using the term vaporization, I'm not telling evaporation, okay, because evaporation is a natural phenomena. And if I undergo boiling of a liquid, I am applying heat externally. So it's an external factor which is affecting the change of the state. The temperature at which a liquid boils and changes rapidly into the gas at atmospheric pressure is called boiling point of the liquid. So water boils at 100 degrees Celsius, we all know. So what happens at this 100 degrees Celsius? At this 100 degrees Celsius, water changes to its gaseous form or steam. But please keep in mind, you will be required to know in higher classes that at this temperature, 100 degrees Celsius, liquid and the vapor phase attains equilibrium, or I can say the liquid and the vapor phase coexist. So the liquid phase also existing and the vapor phase is also existing. So there is a conversion, rapid conversion from a liquid to the vapor and the vapor to the liquid. Now the moment I am telling that liquid to vapor, I understand it's vaporization or boiling. But vapor to liquid is condensation. And both these phenomena, when occurs at the same rate, the system is said to be in dynamic equilibrium. Okay, so let us see the next page where we are going to see what is happening when condensation takes place. When condensation takes place, the liquid changes to the vapor state, of course, by cooling. So, I'll say the gaseous form changes to the liquid state, of course, by cooling. So, I correct it. The gas phase changes to the liquid phase by cooling. And this phenomena is known as condensation. Process of changing of the gas to the liquid by cooling is known as condensation. Okay. So now we have seen what is happening. Again, for our revision, we can say a solid can get converted to the liquid and the process is known as melting or fusion. Liquid can get converted to the gaseous form and the process is known as boiling or vaporization. Now the gaseous form can get converted to the liquid, which is known as condensation. What happens if a liquid gets converted to solid? This is known as freezing or solidification. So let us see what happens in freezing or solidification. The process of changing of liquid to solid by cooling is called freezing, and it is also known as solidification, which is the reverse of melting. If in melting it is required to apply heat, for freezing it is required to cool the liquid. By lowering the temperature, what is happening? The kinetic energy is reduced, the particle movement is reduced, and hence the particles are capable of coming closer and increasing the interparticle forces of attraction, thus changing the state of the matter. So, moving to the next page, here we can see whatever we were discussing, that solid state getting converted to the liquid state, getting converted to the gaseous state, and how? By heating, by cooling. Okay, so next, moving on to the topic latent heat. You know, the term latent actually means hidden. Latent means hidden. What is hidden? The heat is hidden. How? The heat energy which has to be supplied to change the state of a substance is known as latent heat. Why? Because when you are applying this much amount of heat, it does not raise the temperature. See, initially, when I am telling that I want to melt the solid to the liquid state, and I want to change the liquid to the gaseous state, that means I'm talking about the freezing temperature, the melting point, the boiling point, all these things. If I say solid to liquid, then the melting point, liquid to solid, then the freezing point, liquid to gaseous form, then the boiling point. Now at this point, the temperature remains fixed. There is no change. So what was it? When the liquid was boiling, did it start boiling all at once? No. When you have applied heat, gradually there was a change in the temperature. There was increase in temperature. And when the liquid started boiling, the temperature remains fixed. If I say water, then the temperature remains fixed at 100 degrees Celsius. And at that temperature, the change of the state is taking place from the water to the gaseous form or to the steam form. So this is known as latent heat, the heat that is remaining hidden and it is not raising the temperature. Why is it called hidden heat? Because the heat that you are actually giving externally is not raising the temperature, does not show the rise in temperature. Where does it go? It goes to change the state of the substance. It goes to overcome the forces of attraction between the particles. So where does it go? The latent heat which we supply is used in overcoming the forces of attraction between the particles of a substance during the change of state. So that is why latent heat does not cause a rise in temperature of the substance. Now, latent heat is of two types. It can be latent heat of fusion or latent heat of vaporization. When I say latent heat of fusion, fusion means what? Melting. So changing from a solid to a liquid state. When I say vaporization, that means liquid to the gaseous state. That is known as latent heat of fusion or latent heat of vaporization. So the heat required to convert a solid to the liquid state is called the latent heat of fusion or latent heat of melting. And from the liquid to the vapor state is called latent heat of vaporization. So let us see them one by one. This is one experimental demonstration where melting of ice to form water, the solid to the liquid state change is being shown where the temperature gradually changes but becomes fixed, where melting of ice means what we are doing? We are changing the ice to the water state. So the latent heat of fusion can be studied by this experiment. We have to take some crushed ice over here. So crushed ice in a beaker and you fix it to a thermometer. And now what do? We note the temperature of ice. It was found to be 0 degrees Celsius. Now we need to use a burner and heat the ice gently. So by using a small flame of the burner, heating it gently, not very high temperature all at once, the ice starts melting to form water and we keep on recording the temperature. After some time, as more heat is given, more ice will melt to form water. But the reading of the temperature remains at 0 degrees Celsius. How long? As long as the entire ice changes to water. So during this process of melting, the temperature remains constant at 0 degrees Celsius. It does not rise. So it shows that there is no rise in temperature during the process of melting of ice till all the ice has undergone a change to the water state, liquid state. The heat which is going to the ice does not increase the temperature and is the latent heat. And so it is the energy required to change the state of the ice to the liquid state, that is the water state. In overcoming the forces of attraction between the solid ice and increasing the interparticle distance, decreasing the interparticle forces of attraction. And now we need to see the latent heat of fusion or melting of ice as a technical definition. What? The quantity of heat in joules required to convert 1 kilogram of solid at its melting point to liquid without changing the temperature. So what is the unit of the heat? Heat is in joules. To convert the temperature, to convert the state of the solid, how much of the solid? 1 gram of the solid. When at its melting point to the liquid without any change in temperature. So these are the key words. You have to say that the heat is given in joules. You are measuring in joules. You have to mention that it is the amount of heat in joules which changes the state of 1 kilogram of the solid at its melting point. to mention at its melting point is equally important. Okay, so experimentally it has been seen the latent heat of fusion of ice is 3.34 into 10 to the power of 5 joule per kg. Okay, so why joule? This much amount of heat per kg of the solid. Okay, so now let us see some more question. Where does the heat energy go? I have already said the heat energy is used up in changing the state of the solid to overcome the forces of attraction between the particles. And this is the reason that the temperature is not rising. Have you tried this thing? That when you hold a piece of ice in your hand feels very cold because it takes the latent heat which is required for its melting. After some time you feel that the liquid, that means the ice had started melting, and you can feel the liquid form as well. Okay, so now let us see the latent heat of vaporization. Latent heat of vaporization is the amount of heat required to change the liquid to the gaseous form. And the liquid to the gaseous form for water to change it to steam is 100 degrees Celsius, showing no rise during the boiling of the water. Thus, once the boiling of water begins, the entire water boils at this constant temperature, which is 100 degrees Celsius, till all the water has got changed to steam. And the technical definition of latent heat of vaporization of the liquid is the quantity of heat in joule required to convert 1 kg of liquid at its boiling point to the vapor phase without changing the temperature. Just as the previous case we have seen, here again I will say for vaporization, changing to the gaseous state from the liquid state, how much amount of heat is given in joule in order to convert 1 kg of this liquid to its gaseous form at its boiling temperature. That means the temperature remains fixed throughout the change of state, and experimentally it has been found for water it is 22.5 into 10 to the power of 5 joule of heat is required to change 1 kilogram of water. And thus we can say that the latent heat of vaporization of water is 22.5 into 10 to the power of 5 joule per kg. That is the latent heat of vaporization of water. And here again, the heat energy supplied to the boiling liquid is used up in changing the state of the liquid to overcome the forces of attraction of the particles. Because to change it from a liquid to the gaseous form, you need to increase the interparticle distance and decrease the interparticle forces of attraction, which you can do by application of the heat that increases the kinetic energy of the liquid particles. And this is the experiment which can actually give you the practical experience of the phenomena, where the boiling of the water starts at 100 degrees Celsius and remains at 100 degrees Celsius till the entire water has got converted to steam and the temperature does not rise. Have you felt that if a little of the spirit is actually you take it or it comes to your hand anyhow, you get a cool feeling? Why is it so? Why does this spirit, even in a very small amount, gives you this cool feeling? Because the spirit needs latent heat of vaporization to change to the vapor state, and it takes it from your hand, and your hand loses that much amount of heat and gives you a cooling sensation. Have you ever marked that the burns that are caused by steam are more severe than the burns that are caused by water. When water changes to steam, it absorbs latent heat. But when steam condenses to form water, an equal amount of latent heat is given out. So water changes to steam, it takes the heat. But when the steam returns back to the water, that is gas to the liquid form, cooling is required. The amount of heat that it has taken, it gives out the total amount of heat for which you get more severe burns in steam than in water. Okay, so what is happening? That the fact that steam contains more heat in the form of latent heat than boiling water. So what happens when steam falls on our skin and condenses to produce water? It gives out this much amount of heat. How much? 22.5 into 10 to the power of 5 joule per kg of heat is given out, and thus it explains why steam is better than boiling water for heating purpose as well. Now what if a gaseous form changes to solid or a solid form changes to the gaseous form? This phenomena is termed as sublimation. So this is the phenomena of conversion of a solid to the vapor phase and vapor to the solid phase without undergoing the liquid phase in between. So the changing of the solid directly to the vapor on heating and of vapor into solid on cooling is known as sublimation. And this process goes on happening directly, and the substance is known as sublimable substance, and the solid substance which undergoes sublimation is also called sublime. It is also known as sublimable substance or sublime. The process is sublimation, and the solid obtained by cooling the vapors is what? The sublimate. The vapors cool to give you the sublimate. Okay, so what are the common sublimable substances? Ammonium chloride is sublimable. Camphor is sublimable. Okay, so camphor, ammonium chloride, these are all common sublimable substances which you can see in your daily life, and you see that on cooling you get back the solid substance. Okay, so it directly changes to solid ammonium chloride when hot ammonium chloride vapor is cooled. Okay, so this is not a very common process, it is a rare process. The common substance which undergo sublimation are what? They are ammonium chloride. What is the formula of ammonium chloride? NH4Cl is ammonium chloride. Iodine vapors are also sublimable. Camphor is sublimable. Naphthalene and anthracene are sublimable. Naphthalene balls, if you keep, you will see after many days, if you see, they have become smaller in size. Where did it go? It has gone to the vapor phase. Now, this is another fact that we need to see, that is, sublimation is provided by solid carbon dioxide or dry ice. Dry ice is solid carbon dioxide. Now this sublimes to the gaseous form, which is carbon dioxide gas, and an activity of this sublimation of ammonium chloride. Similarly, you can do this activity with camphor as well. This is the ammonium chloride which is crushed and kept it in a china dish. This is the funnel which is kept inverted and a cotton plug over here such that the vapors don't escape. The process of vaporization we can see over here by slight heating, and when the vapors move up, they gradually cool down, and what happens that they form this sublimate, okay, on the walls of the funnel. And you can see a cloudy appearance on the inner walls of the funnel, which is the solid ammonium chloride. So this is the case for naphthalene balls, which seems to disappear after some days. And this figure, I'll say to see it very minutely, what is happening. Solid form to a liquid form, melting. Liquid to the solid is freezing. Now liquid form to gas is what? Evaporation or vaporization or boiling, and gas to the liquid is condensation or liquefaction. Now gas to the solid is sublimation, and solid to the gas is again sublimation. Okay, so effect of change of pressure. If temperature is changing the state because of the change in the kinetic energy or movement of the particles, because of the change in the forces of attraction between the particles, pressure is also another factor that can bring out change in the interparticle forces of attraction, the change in the interparticle distance, and hence the change in the physical state. Now, what can happen? If I change the pressure, suppose I say I have to go from a solid to a liquid, that means I have to increase the interparticle distance. What is required is a lowering of pressure. From liquid to gas, what is required is lowering of pressure. If I lower the pressure, then the compactness of the particles decreases and they move apart. So if I have to do the reverse from the gaseous to the liquid state, I have to bring them closer. So what I need to do is I need to increase the pressure. Similarly, from liquid to the solid state, I need to increase the pressure in order to bring the particles closer, in order to increase the interparticle forces of attraction. So that is what gases can be liquefied by applying pressure and lowering temperature. So if they say that how can you change a gas to a liquid, then the complete answer is you need to lower the temperature and you need to increase the pressure. Then only the particles will come closer. If I say I want to convert the liquid to the solid state, the same condition will remain. Lower the temperature and increase the pressure. So the reverse will take place, that is, let us see in the next page what it is. The reverse can take place. Suppose I want to go from a gaseous form to a liquid state. So what did I see? Gaseous form to a liquid state. I need to lower the temperature. I need to increase the pressure. Reverse. Liquid to gas. I need to decrease the pressure. I need to increase the temperature. Okay, so liquid to a solid state, bringing the particles closer. What will happen? I need to increase the pressure. I need to decrease the temperature. Okay, so I'll just rectify over here. What I need to do, liquid to a solid state means increasing the pressure, decreasing the temperature. Okay, so again, solid to a liquid state. This solid to a liquid state. So what I need to do? I need to increase the temperature. I need to decrease the pressure. Always remember, increasing the temperature increases the interparticle distance. Decreasing the temperature brings the particle closer. Increasing the pressure decreases the interparticle distance, and decreasing the pressure, what happens? Increases the interparticle distance. Okay. So here evaporation process, we know evaporation is a natural phenomena. What has to do with it? See, we have seen what is vaporization, what is boiling. So we should know what is evaporation. Now, Evaporation is the change of the liquid to the vapor phase. Now remember, there is a slight difference between boiling and evaporation. These are the factors affecting evaporation: temperature, surface area, humidity, and wind speed. Temperature, of course, if the temperature is greater, then the rate of evaporation will also be greater because more number of particles will move to the vapor phase from the surface. So what happens in evaporation is it is a natural phenomena, but if you increase the temperature, it becomes faster, or in hot days, humid days, the rate of evaporation changes. But in hot and dry days, again, what happens to the rate of evaporation? Let us see. Evaporation is also a surface phenomena. Okay, so boiling is a bulk phenomena and evaporation is a surface phenomena. If the surface area is greater the surface area, the rate of evaporation also increases. Humidity has inverse relation with evaporation. If the air outside is already humid, now it cannot keep more of the water particles. So what happens in a humid day, you will see it takes more time to dry your clothes at home. But in a dry day where it is very sunny and it's dry, the clothes at home get dry faster because more water particles move to the vapor phase and the air holds those water particles. The speed of the wind, if it is more, then rate of evaporation also increases because the air part which contains the water droplets, it moves out and now more air can hold more of the water particles. So these are the factors that affect the rate of evaporation. So these are explained one by one. Whatever I have said is explained here. So now cooling, that is evaporation causes cooling effect. Haven't you seen that when when you are sweating profusely and you come under the fan, what happens? You feel cool. Why? Because your sweat gets evaporated and you feel cooler because evaporation causes cooling effect. There are many phenomena that you can see where naturally you can see that evaporation causes cooling effect. Why is it so? The cooling caused by evaporation is based on the fact that when liquid evaporates, it draws or takes the latent heat of vaporization from any object which it touches. By losing the heat, this substance gets cooled. Okay. If we put a little spirit or ether at the back of your hand and wave it around, the spirit evaporates and your hand feels cooled. Why? Because for the evaporation of the spirit, the latent heat is taken from your hand, and so your hand feels cool. Thus, evaporation causes cooling effect. Have you seen that during hot summer days, if you keep water in a matka, which is known as earthen pot, the water remains cool. Why? Because this earthen pot contains very small tiny pores and water drips. Okay, it drips out. The water sweeps out, it drips out, and what happens is the water comes to the surface and gets evaporated gradually, taking the latent heat from the earthen pot, okay, and the remaining water. Thus, the remaining water inside the earthen pot becomes cool. So, this is known as seeping of water also through the pores. So, let us see. Some of the water continuously keeps seeping or dripping through these pores to the outside of the pot. and this water evaporates, continuously taking the latent heat from the earthen pot and from the remaining water inside the earthen pot. Thus, the remaining water inside the earthen pot becomes cool. At many places, people often keep what they keep a wet cloth, you will see, around this earthen pot. Why? Because the water inside will remain cool for longer time. They change the wet cloth as soon as it becomes dry and again wets it. Okay. Now, at many places, especially in villages, people often sprinkle water on the ground in front of their homes during hot summer evenings. Okay. Why? Because that water will evaporate, giving actually a cooling effect. Okay. Perspiration or sweating that we have told what happens. So why should we wear cotton clothes during the summer? It keeps us cool, it keeps us comfortable. Why? Because the sweat that you get, cotton is a good absorber of water and it absorbs all the sweat from your body and exposes it to the air by the process of evaporation, thus giving you a cooling effect. So synthetic clothes will not give you this cooling effect during the summer. These are the experiments to show the presence of water vapor in air. Okay, so another example over here, you see that a fan increases the rate of evaporation of the sweat and gives you that comfortable feel. A desert cooler cools better on a hot and dry day. Why? Because higher temperature, what happens? Increases the rate of the evaporation. And if the rate of the evaporation increases, the cooling effect is also greater. Now here we can see that we can sip hot tea or milk easily from a saucer, a plate. Have you seen villagers have this habit? Many people, if you have to actually sip milk or tea, maybe due to less of time, what will you do? You will pour it in the saucer and the surface area increases and so it cools faster because evaporation depends on the surface area. Greater the surface area, greater is the rate of evaporation. Now to show that water vapor is there in air, it's very common example. You take some crushed ice in a tumbler, say it can be a steel tumbler, and what happens after some time, can't you see the tiny drops of water at the outside part on the body of the tumbler? Why? What happens? The air around the steel tumbler contains water vapor. Now, when it comes in contact with this cold surface, what does it do? What happens? They condense to form tiny drops of water when it comes in contact with the steel tumbler. So the air outside, this is the air outside, it contains water vapor. These water vapor, when they come in contact with this cold surface, it's a just change in state that happens, and so this cooling effect gives you this drops of water on the outside surface of the tumbler, and thus it proves that water vapor is present in air. The two more states of matter in my first part of the content, I will say. If you follow the playlist, you will see the first part contains plasma and the Bose-Einstein condensate. Okay, so apart from the solid, liquid and the gas, the plasma is a mixture of free electrons and ions, and it occurs naturally in the stars, including the sun. Inside the stars, what happens? The temperature is so high that the atoms automatically break, and some of the electrons, they break away from the atoms, converting the rest of the atoms into electrically charged particles called ions. So this is the plasma state. And plasma can also be made on Earth by passing electricity through gases at very low pressure. Okay. How? Taken in a glass tube which is known as a discharge tube, where the pressure is kept very low. Plasma makes a fluorescent tube on neon sign bulb to glow. So this was the plasma state. Now you know that Indian scientist Satyendranath Bose, we are gifted. India is actually gifted us so many scientists, gave birth to so many scientists. In the year 1920, one of them, Satyendranath Bose, did some calculation for the fifth state of matter. And it was said the Bose-Einstein condensate, or BEC. It was named after the scientist. Okay. Now it was obtained how the fifth state of matter, the BEC, was achieved by three scientists. These are the scientists by cooling a gas at the gas of extremely low density. Okay, so now you need not go into the details of the plasma state, of the details of BEC, but just keep in mind that these are the fourth and the fifth state of matter.